is Howard Vernon. I am the land manager with Tokeland Oil and Gas, and we're based in Tulsa. And also serve on the AIPRO board. If I haven't met you yet, please say hello today. We'd love to get to know everyone better. I'm going to introduce our first speaker today, Mr. Bruce Randall. I've gotten to know Bruce over the last year as he's a friend of the Nickel family that owns Tokeland and office in the same building in Tulsa. I heard Bruce's presentation recently in Oklahoma City at an OEPA meeting, and I really thought highly of it and wanted to invite him here to speak to AIPRO. Bruce has accumulated almost 40 years of experience in the oil and gas industry, and after selling his bootstrapped E&P company that operated in the Texas and Oklahoma panhandles in 2012, he has worked exclusively on his current company, which is Coiled Tubing Specialties. I hope you find his presentation on how our industry can better frack very intriguing and persuasive, as do I. And please take notes for questions as time allows at the end, or if not, you can catch him during the break and pick his brain. Without further ado, Mr. Bruce Randall.
Thank you, Howard. Can everyone hear me all right? Okay. I hadn't planned to use this. This just came across from the Wall Street Journal. The American shale boom is slowing as innovation plateaus. And just when shale's importance in global markets has reached new highs following an attack on the heart of Saudi Arabia's oil infrastructure. So innovation has plateaued. My response to the Wall Street Journal is not so fast. Coiled Tubing Specialties is basically 3 engineers. Between us, we have about 120 years of experience. Or as my recently deceased father would have said, we're all old enough to know better. But for about the last 7 years, we've been working on a new technology that we think could be a game changer, and that's what I want to share with you today. Right now, we're currently prosecuting about 50 different IP actions everywhere from China to Australia to Argentina, of course, U.S. and Canada, everywhere that might have a shale. So we've got quite an IP portfolio that we've put together these last 7 years, but probably the most valuable thing we own is a proprietary frac modeling study by Dr. Mike Smith. If any of you have ever sat in a frac van and watched a Nolte Smith plot on the screen, he's your guy. But I want to share with you some of the results of that proprietary study today. The technology that we're employing is radial hydraulic jetting, and it has a bit of a sordid past. Some of you in here may have even tried it before. Bottom line, it was a po' boy post hole originated by a guy named Carl Landers in Kentucky. The conclusion of most who tried it is it just ain't oil field. A company in Houston, Randall Drilling, has really perfected its application in vertical wells. Most of their clientele is international. But what we want to do is to be the first kids on the block to be able to deploy radial hydraulic jetting in horizontal well bores. The outline of my presentation today, I want to present 3 premises. I want to talk specifically about the problems of fracking we face today. I want to introduce to you a new paradigm. And I've done a little work here in the last couple of weeks on how this might apply to the Fayetteville Shale. First, let's get our terminology straight, particularly when we're talking about frac hits. But I'm submitting to you the terminology is like football. You have a strong side and a weak side. Your fracs, when you have a frac hit, or the new term today is fracture-driven interaction, is going to head always to the weak side. And if you have microseismic data as represented by those blue dots, generally what you see is that everything goes to the weak side, and the strong side of the reservoir, where you have stronger pressures, greater hydrocarbon saturations, where you really want to be draining from, you don't touch it. Let's talk about our job, what we're setting out to do. Say you got a section of Lower Fayetteville that you want to frac, and the pay's 100 feet thick. So your job is to bust up 64,000 acre feet for almost 3 billion cubic feet of rock. Ideally, what we'd like to do is drill one horizontal well and frac it in stages. And of course, none of our stages are going to cross a lease line. But we're going to bust up that rock in a series of hydraulic fractures. For that 100-foot thick pay interval, if you end up spacing that at 9 wells per section, then the volume of rock you need to bust up is about 2.6 times the volume of Minute Maid Ballpark. And I'm talking about the whole facility. At its peak of 93 feet high, over the whole parking garage and everything else, it covers about 29 acres. That's the volume that one of 9 wells has to bust up. Unfortunately, what happens is something like this in a lot of cases, particularly in the most prolific producing zone in America today is the Wolfcamp. And the Wolfcamp is notorious for busting out a zone up. So what happens is you have a lot of unfracked pay below you, and you're going way out of zone upwards. You're having frac hits and leaving unfracked pay on the strong side of each hit. And what I'm submitting to you today is we've got sideways once. Now we need to get sideways squared. What I'm wanting to do is, before you frac, jet an 1.5-inch diameter mini lateral borehole into your pay zone, generally perpendicular from the lateral of the parent well bore. Today, in vertical wells, they can go out to 300 feet, and that's, for modeling purposes, the length that we use. One of the most important things to remember is if you do this, you'll be initiating your fracture within the pay now from a line source instead of a bunch of point sources in the casing. You now have a line source within the pay from which to initiate your fracture. Later I'm going to show you how our jetting assembly and whipstock mates with a patent pending sliding sleeve system that's ported and self-orienting that is pretty slick. I've got three premises I want to start with this morning. What I think we've done in our current practices, particularly with plug and perf, is we've become very efficient at stringing together a bunch of very ineffective fractures in some very lousy rocks up and down the lateral. I mean, we're out there with a stopwatch. Usually we've got two wells going on at once. We're perfing one and fracking the other, and then we switch. But if you've ever seen that operation, it's like synchronized swimming in the Olympics, right? I mean, we have got it down. We are very efficient at fracking. The question is, how effective are we? At a $76 billion cumulative total well cost for 2019, and if we assume our frac costs are half of that, and that's a pretty conservative assumption, we're going to spend $38 billion this year fracking wells in the domestic U.S. If 50% of that is wasted by fracking out of zone, we're talking about a $19 billion a year problem. I would submit to you that problem is a major contributor to our current average break-even costs of 48 to 50 bucks a barrel. My third premise is that ultra-deep perforations, and that's what we're calling these 1.5-inch diameter, 300 feet long mini lateral boreholes, is ultra-deep perforations. That they can keep fracs in zone for substantially greater lengths, such that production rates and expected ultimate recoveries can be obtained with significantly fewer wellbores. Think about this. In what situation am I better off with a conventional perforation that at best may be 24 inches long instead of one that is 300 feet long? It's almost analogous to the question, when am I better off with a vertical well instead of a horizontal well? My career started in 1980, right after I married that little banker's daughter up there to the top right. I wanted to include that to at least demonstrate there was a time I had hair. But what we were focused on at that time is conventional rocks, or maybe we were getting into the near type regime from this slide by George E. King. The thing to note is that permeability scale on the bottom is a logarithmic scale. So basically we're dealing in the range of 0.1 to 100 millidarcies. And what George is showing on this slide is this is the frac length, or fracture half length actually, of a wing length that you have to have a profitable gas well as you start to lose permeability. This is that same plot, but what I've done is I've superimposed the shale plays that we're in today. You can see the Eagle Ford, for example, is kind of close to what we were doing in the 80s. But then you start getting into the Bakken, the Marcellus, the Barnett, the Woodford, the Haynesville. You're off the chart. George has called them near tight, tight, very tight, extremely tight. What do we call this stuff now? Tombstone? But look at the bottom scale. No longer are we talking about millidarcies in perm. We're talking about microdarcies. When you get to the Haynesville, you're talking about nanodarcies. Folks, what we're calling pay today is what we hoped to get back in the 80s for our frac barriers. Let's look at our problems. Our first problem is a directional problem, or fracking. Second is a dimensional problem, or going out of zone. It's obviously a dollars problem. And lastly, I want to talk about it's a dam problem. But notice I left the N off. Let's talk about it being a directional problem. These are from my friends at NCS Multistage, where these are actual wells where they place tracers in each frac stage. If you look at the right, that's what we intend to do. We intend to get coverage on both sides of our lateral. But you look at what we actually did in this situation, we only had a couple of stages penetrate the strong side of the rock. So those boxes with question marks, all that represents is stranded reserves. Really, from a reserves recovery standpoint, since we didn't get much into the strong side, we've done less than a half-baked job. Directionally, we're completing our well from the toe to the heel here in this block of pay zone. And we're marching along, and all of a sudden, boom, we have a frac head in stage in there in purple. And we hit our parent well bore. Frac heads, this subject dominates every technical conference you can go to. I started keeping a graph of how many technical papers published every year are dealing with frac heads. As of April, we got up to 256 papers, but what I want you to notice is the rate of them. In the last few months, we've been generating a technical paper every 1.8 days dealing with frac heads. When I update this at the end of the year, I think they're going to be like vitamins. We gen one a day. Let's talk about the dimensional problem. This is a Haynesville well that we have microseismic data on. And up to at the top right, you see those red boxes, basically with little or no frac activity going on, because everything went to the east side of this wellbore. So those red blocks represent stranded reserves, but look down at the bottom right. We've got a lot of unaffected pay, unstimulated pay in the Haynesville sea layer, because a lot of our job went up out of zone into the Bossier, way up there. We know this happens because we've got Haynesville wells that produce Cotton Valley water. So this becomes a dollars problem. How much money did I waste in hydraulic horsepower, water, proppant, and additives up into the Bossier? And what do I have to do now to recover those stranded reserves that I left on the west side of the wellbore? Do I have to drill another well to capture those? A few months ago, we achieved patent pending status on a method I'm going to show you to address this problem. It's no secret anymore that our child wells aren't performing as we originally predicted. This is an interesting slide. This is from my friend Richard Spears at Spears and Associates. And what you see with the layers there is 2019 actual activity and then their projections of reservoir feet completed by quarter. And notice it is still going up and to the right. On the red line there, I've overlaid the Baker Hughes actual rig count. So while rig count is declining, our completion of reservoir feet is still increasing. Well, we know the reason, and I know these are hard to read, but we know the reason is we're drilling longer and longer laterals, and not just in a few basins, in basically every basin. We're increasing frac stage counts in every basin. We're cramming in more and more sand or proppant per lateral foot. We're using more and more fluid volumes at higher and higher pump rates. So if we're doing all this more and more, why does our monthly production trend look like this? Look at my question there on the bottom right. Has the ever-increasing percentage of child wells in the nation's horizontal portfolio, with their epidemic onslaught of FDIs or frac hits, is that finally showing up? You know, we're to the point that 70% of what we drill is a child well. Dad would love this slide. If we're losing a nickel bale, perhaps the answer is not to haul more hay. Let's talk about what we're trying to do when we're fracturing. And this is a vertical well. This is another George King slide. And we see out on the far right where I've created this hydraulic link for my fracture. That's how far my frac fluid went. My pad, if you will. And then I start throwing proppant in the mix and I achieve that prop length. And I did all that so that crosshatched area within my pay zone gets stimulated out to that productive length. So yeah, I go in and out of zone, up and down, maybe some small multiple of the thickness of the pay itself. But everything here is still working for me. I had to create that much hydraulic length to get that much prop length to get that much productive length. That red area up there is what we might call the cost of doing business. Here's a horizontal Wolfcamp frac model done by Mike Smith. And what I did is I said, Mike, I want you to do some modeling for us on actual frac jobs where you've had all the data and you've modeled those jobs in horizontal shale completions. And because you've had all the data, you know that your model nails it. Well, here's a model of a Wolfcamp frac. And the frac goes way up further than this is even showing. But most of our money goes up out of zone. And it's no longer working for us. It does nothing to help us to create that maybe that 400 feet of wing length. And notice we're talking about proppant concentrations in the various color schemes there. How poorly connected, even what I did stimulate, how poorly connected that is to the wellbore. We know this is true from microseismic data in the Wolfcamp. This is from SM Energy. And they're showing showing they go almost 1,500 feet up out of zone. Maybe that's why when we show a wine rack presentation, they're so well stocked. My gosh, spacing of 264 feet, 189 feet. These are wing wings. Heck, on 3 out of 4 of those, my jetting hose is longer than that. Next, it's a dam problem. This is interesting. A couple months ago, Rystad Energy came out with a prediction of how much water we are going to use in hydraulic fracturing for 2019, 2020, 2021. For those 3 years, we're going to use 16.9 billion barrels of water. And I thought, boy, Brucey, that's a big number. How big is that? Well, that's within 1 billion barrels of the contents of Lake Eufaula. You know, I know methane emissions is a thing, and we're doing all we can to address that. This is the issue that concerns me for my industry. So you've done that one. I don't think it matters how we generate UDPs before we frack. I don't care if we use napalm or kryptonite. But I think that's what we've got to do. We've got to reshuffle the in situ stress depth within the rock. And when I use the term radial hydraulic jetting, actually what we're using in our system is a constant flow of abrasive. So it's really abrasive jetting. But at its essence, what we're dealing with are in situ stress issues, and I'm submitting to you today, they demand an in situ stress solution. So what we need is a paradigm shift. I agree wholeheartedly with Daniel Yergin's statement about George Mitchell. That his fracking technique is so far the most important and the biggest energy innovation of this century. And I'm not up here saying that we're doing anything of that magnitude. I'm not worthy to carry George Mitchell's gym bag. But I think we've got to use radial hydraulic jetting and to go sideways one more time to start controlling our frac treatments. For the sake of time, I'm not going to show this video, but in that middle video there demonstrates hydraulic jetting through that sandstone at a rate of 11.8 feet per minute. Our target rate is 6 feet a minute. So we want to use UDPs, we want to be fracking our pay zone from the inside out from a line source. We want to increase our exposure now to the strong side of the reservoir. Basically what we're talking about here is frac steering. And we're leveraging rock mechanics to optimize effectiveness, and I'll show you what I mean by that. In a half section, this is what it looks like. Those red dashed lines are our UDPs. We jet those for each stage, and then we frac. And we emanate our frac from those UDPs. I'm not talking about doing this a little bit. Here are some calculations assuming each UDP is 300 feet long. And what I'm showing here is, depending on your lateral length and what your stage spacing is going to be with these UDPs, you're going to be jetting UDPs that have a cumulative length that's multiple times that of the lateral borehole. What's really interesting is the research that's being done when you first jet a mini lateral borehole and then you frack it. How well does that control the direction of the frack? But all the research that I can find on that issue is being done, and it's all recent, but it's all being done in China. This is what I think is the most important slide I'm going to show you today. There on the far right, this is a rifle view, if you will. You're looking into that horizontal borehole. And those lines to each side of the hole are of equal stress magnitude. They're not quantified, it's just for depiction. But what happens in the case where the greatest principal stress is in the vertical due to overburden? And that's where we live, right? When you have that greatest principal stress in the vertical due to overburden and you jet a horizontal hole through the rock, then you induce strong compressive forces on the side and strong tensile forces at the top and bottom. That's just rock mechanics. Here to the far left is showing you round holes, originally round holes, that were jetted in the pillar of a mine. So again, your greatest principal stress is in the vertical due to overburden, but look what happens to the shape of those holes. They become ovular because of the strong compressive forces on the sides. What's that look like in 3D? Well, you generate a hole in your pay zone, and now you've induced continuous weak points at the top and bottom of that mini lateral borehole. Now when I introduce my frac slurry, instead of going either up or down, the preferential direction for my frac slurry is to go out, to go along the path of that mini lateral borehole. Now here's some results from Dr. Smith's modeling study. This is of the Leonard Formation in the Delaware. Up at the very top, there in the center, you see the profile of the actual job that was pumped. Now down here at the bottom, you see where I've taken that profile and converted it to grayscale. Note too, the red bracket there of the actual thickness of my pay zone. That's where I want to keep my frac slurry. Now down at the bottom, this new superimposed stack of colors, is what Dr. Smith modeled if you first generate a mini lateral borehole in that same zone and then you frac it. Notice how well your frac slurry now stays in the pay. Over to the far right, you see where the proppant is stacked up within that frac. So you have excellent connectivity back to the wellbore along that mini lateral. The end result is you just about double the length of the frac. One constraint I put on Mike when he did his studies, I said, Mike, after you model generation of mini lateral and then frac, you pump the same frac slurry, the same frac job that was actually pumped. So we're comparing apples to apples. What Mike discovered when you do this is that your injection pressure to pump that same frac job is significantly reduced. And what you could have done is put in a lot more proppant to cover the pay. The bottom line for the Leonard is where it is customarily developed at 5 wells per section. Now you can get the same reserves and really probably better production rates because you have better connectivity. You can get that same performance with 3 wells per section instead of 5. Remember our wolf camp? This is the actual job that was pumped and that Mike modeled. This is what happens if you jetted a mini lateral first before you frack. You don't do quite as well here as you did in the Leonard. You gain about 50% of frac length. But look how well you're connected to the reservoir. Look how poorly you were connected with just a conventional frac. So for the dimensional problem, what we've got to do is we've got to disrupt the in situ stress of the rock. Our second generation tools, we hope to be steering the path of these ultra deep perforations. And we know we've got to be able to do this for a contiguous distance out from the wellbore. This is what Mike told me after conducting a study. Bruce, this is how we should have been fracking wells all along. Quite frankly, that's what's given me perseverance to endure. And to develop a system that can rapidly, repeatedly, and reliably generate ultra-deep perforations. So we can steer the frac both in its direction and dimensions. Remember our frac kit depiction? What do we do for the next stage when we know we've hit the parent well? This is what we do. And this is what we just got patent pending status a couple months ago. We're going to jet a UDP in the opposite direction to the strong side and not do anything on the weak side. And we're going to frac that strong side stage from the inside out. So our approach for frac kits is to use the UDP's direction. Also, you could go and generate those UDPs on the strong side, then walk away. You don't need a frac crew out there right then, and produce those UDPs and further deplete the rock around them and further weaken the rock fabric around each UDP and make it the even more preferred path for that frac slurry to follow. We're watching very closely developments from companies like Microseismic Heat and Seismos. What I'd love to see is that we're running real-time microseismic on each frac stage, and then you contour the next stage's UDPs based on what you just learned. To complement the development of our tool string, we've come up with a sliding sleeve that is self-orienting. That purple strip there at the bottom is a weighted belly. So when you run these in your casing strings, they have swivels on each side and centralizers on each side. Well, that weighted belly is going to find bottom. You've got ports that you've built in that orient perpendicular to the azimuth of the lateral. And we've got above and below our packer, we've got pressure sensors. So you're getting real-time pressures. How does all that work? How does that come together? Well, let's say you go in and you open the sleeve and you jet a port to the east and you shut down for a minute and you find out you have a pressure of 3,000 pounds. Next thing you do is you're starting to jet your westerly port in the opposite direction, and all of a sudden your penetration rate's picking up. So say at 80 feet or so, you stop and shut down and you realize your pressure's only 2,300 psi. So you're seeing a significant difference there. So you stop. You know you're building a frac hit if you keep jetting westerly. So you can leave that easterly port open, close off the westerly port, and produce that UDP through that sleeve. You could move up the casing string and with our assembly jet through it and jet another easterly port to leave producing if you wanted to. This is a depiction, the concept drawing of our tool string. Basically, we've taken the existing radial hydraulic jetting technology and got Western with it and put things in like a whipstock and slips and a packer assembly, and we designed it to run on E-coil and to mate with our sliding sleeve system. Remember our Leonard case where we were going from 5 wells down to 3, and for lack of a better term, call them super wells. How would we actually complete those? We might have 29 clusters at 300 feet. We're generating 3.3 times our length of the original lateral. Jetting time to do that calculates to be about 48 hours. Let's say that your cost to do a conventional horizontal well is $7 million, and you were going to have to use 5 wells per section. Well, now you only need 3 wells, but you got some additional costs for all that hydraulic jetting. Say that's $1 million. Well, your bottom line comes out to a 31% reduction in total build cost. Again, we're not doing this a little bit. It'll be multiple times the length of your lateral. Here's my summary questions. Does the potential to extend frac dimensions within the pay by itself warrant testing this technology? Or the potential to influence frac direction by itself, make it stand up? Or just the potential to increase connectivity or to reduce the water required? We think all 4 are a pretty good deal. Let me go past that. We talked about frac kits. I've looked at, how am I doing on time? Okay. I've looked at applying this to the Fayetteville. I'm a Fayetteville expert for the total length of 2 weeks now. So qualify what I'm about to say. But this is from an excellent paper I found by some Southwestern Energy guys. It was a great tutorial for this novice. But as we all know, it's that lower Fayetteville 2 interval that's really the sweet spot on a pay. What happens in a lot of cases is when we frac, we have hydraulic length that goes through the entire Fayetteville section. You've really got pretty good barriers, natural barriers in a large portion of the field both above and below the Fayetteville. Getting proppant, when you place your lateral in the lower Fayetteville, getting proppant up into the upper Fayetteville is a question. When I believe it's on the eastern side of your field, if you lose that Hinesville line barrier below you, look at the stress profile there to the left. Everything below you is weaker than your pay zone. So guess where your fracture is? Right now, I believe in a lot of Fayetteville sections, you're developing those on 9 wells per section. If you do basically the same math that I showed you in the winter, I'm saying that you could get that with no more than 5 super wells. Again, you're going to be jetting 3.3 times your lateral length for each well. The math that works out on that, of course, proportional to the winter example I showed you, but I'm saying that you could do that for a 31% reduction in total well cost to develop an entire section. That's even using an extra $1 million per well to do your jetting. For the sake of time, I'm not going to go through this next set of slides, but I want you to know, I think there's some very obvious things that you could do in recompleting Fayetteville wells. Where you know you've had frac hits and you've walked away from an undepleted or uncompleted strong side, you could go back in those wells and jet laterals into the strong side. If some of your older wells had wider stage spacings, you could go in and jet UDPs and stimulate between stages. I think there's a lot you can do with UDPs to get up into the upper Fayetteville if you've not got into it in your original completions. If these recompletion efforts prove out, I think it changes the ability to drill profitably Fayetteville wells now. For example, one thing I think you could do is jet a lateral, land your wellbore in the middle Fayetteville, jet a mini lateral out 300 feet in each direction from that wellbore, and bust through the middle Fayetteville and complete in both the upper and lower. That middle Fayetteville layer is only 60 feet thick, but if you had trouble with that single lateral, you could do something like this and jet directly into the upper and the lower Fayetteville. The distances to get there are well within our 300-foot range. This broke my heart when I saw that. I think there's things we could do to fix this, even at current gas prices. With that, I'll open it up for questions. Yes, sir.
I assume that everything you've shown us is modeling. I think Mike did some modeling for us.
Mike Smith. Mm-hmm.
Can you give us an idea of what kind of rate he was using in his model and sand concentrations, if any? 100 barrel a minute, 50 barrel a minute, or
Yeah.
did he do levels of each, or to get that data?
Mm-hmm. I can send you the actual frac jobs that were pumped, which he repeated in his model. I have them in a slide deck. And I will say, you'll find there was nothing special about them. I mean, it's pretty much slip water and a lot of hunting mesh. Yes, sir.
Another question. So, as an operations person, I see all kinds of boogers out there,
Mhm.
if you will, in doing these 300-foot laterals, abrasive with, and you mentioned whipstock.
Mhm.
How exactly would that work? And the next question, then all in one, is with the ported slide sleeves that are oriented, how does the whipstock calculate in there? Where is that used?
Anywhere you want to make a casing exit, you can. That's one thing. When I used the original Po' Boy postal slides, they were using really tiny little jetting hoses, like 1/4-inch ID things, working everything through their production tubing. Our jetting hose is a 3/4-inch ID.
Coil.
Well, that's a great point. No, it is not coiled tubing, but when you get into 3/4-inch ID, 1.1-inch OD, it has a working pressure of 15,000 PSI. You can get Western with it.
Right.
And you are, like just like you said, you are now in the realm of smaller ID coiled tubing sizes.
Bruce talked about that steerability or orientation. Understand how you get it started the way you want it to go. How do you keep it going?
Excellent question. Theoretically, you got to remember, in this process, you have no mechanical interface with the rock. You're never touching that rock with the tip of that jetting nozzle like you would be with the bit. And when you're drilling, right, it's that mechanical interaction of the bit with the rock that kicks you off quickly. So in theory, because you have no mechanical interaction, you should go straight in the direction that your hydraulic jet is focused. What I talked about as far as Gen 2 is a system where you have 3 nitinol wires that are built into the body of your jetting hose. Those are nickel titanium alloy wires that they're very unique. And when you put an electric current through them, instead of expanding like copper or any other normal metal, these contract. And they contract very precisely, proportional to the current you put through them. So if you put a geospatial chip up near that jetting nozzle, like what's in your iPhone, and you can vary the current in those 3 wires, you should be able to steer it wherever you want. And we've patented that, but again, we're not there building that, ready to run that now. Good question. Yes, sir.
Using for your jetting, or you using 100 mesh, or what are you using
Yeah.
for your material?
Yeah, we've designed our nozzle to have the throughput capacity to handle about 1 pound per gallon 100 mesh in a guar gel system, just like you would hydraulically perforate casing. Good question.
Do you have any mechanism to keep you on depth, or are you using a collar locator or a mechanical collar locator or anything to get you to your higher perforation depth?
Yes. We can run a gamma ray CCL at the end of the assembly. We can run a mud motor. We've designed the system to have hydraulic, electric, and fiber optic capacity from stem to stern. Yes, sir.
So have you done any work with diverters trying to help you in these laterals, or you done any modeling with diverters in any form?
That one slide I skipped was a company called NewTek, and they have a product called InfuSeal. Fascinating diverter. You can pump it into a formation, and it basically sets up like cement. Has a 5,000 psi differential holding capacity. But when it's subjected to any mechanical shear, like if you have a casing full of it and you move your coil through it, once you shear it, it goes back to a liquid. But out in the rock, where it's stationary, it's like cement. The only thing that degrades it is time and temperature, and it does degrade and come back. What I'm waiting to see from NewTek is this month is their first field test. And I'm waiting to see retained permeability tests. But yeah, what you brought up is the key. If we're going to go into a well and recomplete it,
That's right.
to be able to squeeze off everything on top of us, frack down the annulus of the coil and the casing, and be able to do all our work in a single trip. You know, that's a piece of cake in a new well completion, but in a recompletion, you're right, that's the key.
And especially where you completed pressures and
Fortunately, we'll be able to read those in real time with our e-coil and our pressure sensors in our tool. Yes, sir.
Bruce, with this microseismic, are you able to identify where your device finally stops? How precisely can you locate that?
That's a good question. What you're measuring with microseismic is basically miniature earthquakes. And you have shear going on in the rock. It may or may not be directly caused by your frac fluid. It may be caused because you have frac fluid over here expanding the rock, so you're popping it over here. So it's a proxy, if you will, from where your frac fluid is going. But and I think now they're getting pretty close to real time. They still have processing time before you can see it. But I think there will be a day where you're pumping along and you see that cloud heading to your parent well that you can shut down before you hit it. Okay. Thank you.
Thank you, Bruce.